Picture this: a spacecraft, alone in the vast emptiness of space, begins its final descent toward the surface of an alien moon. But unlike any landing we've attempted before, there's no sun here, no gentle glow on the horizon, no reflective surface to guide its way. Only an endless, profound darkness, deeper than any night we've ever known. This isn't a scene from a movie or the pages of a novel. This is the real, breathtaking challenge that scientists and engineers are tackling right now as we prepare to explore some of the most mysterious and compelling worlds in our solar system. We're talking about moons like Europa, with its hidden ocean swirling beneath a shell of ice, or Titan, where rivers of methane carve through valleys under a hazy orange sky. These are places that could hold answers to one of humanity's oldest questions. Are we alone in the universe? But to find out, we have to land there. And that means touching down safely in environments where light has never reached, where cameras are useless, where temperatures plunge to hundreds of degrees below zero, and where a single misstep could mean mission failure. It sounds impossible, right? Yet, this is exactly what the next generation of space missions aims to do. In this video, we're going to pull back the curtain on how humanity plans to achieve the unbelievable landing in total darkness on distant, alien moons. We'll explore the revolutionary technologies being developed right now, from artificial intelligence that can think on its own to sensors that see using sound, heat, and lasers. We'll meet the brilliant minds turning science fiction into science fact, and we'll uncover why mastering this incredible feat could change everything we know about life, the universe, and our place within it. So settle in and open your mind to what's next, because we're about to journey into the darkness, and what we find there might just light up the future of exploration itself. Think about the most profound question humanity has ever asked. Are we alone in the universe? For centuries, it's been a subject of pure speculation and philosophy. But now, for the first time in history, we have the technology to go out and find a real, tangible answer. And some of the most promising places to look aren't planets at all, but the moons orbiting the giant planets in the outer solar system. Worlds like Jupiter's Europa, Saturn's Enceladus, and Saturn's Titan are no longer just points of light in a telescope. They are dynamic, complex worlds that have become the prime targets in our search for life. Each one is a locked treasure chest, and landing on them is the key we need to finally open it up. Europa, for instance, is a frozen world crisscrossed with cracks and ridges, but beneath its icy shell, scientists are almost certain there lies a vast, global saltwater ocean. This ocean is thought to contain more than twice the volume of all Earth's oceans combined, and it's kept liquid by the gravitational tug of war from Jupiter, which heats its interior. Here on Earth, we find life thriving in the most extreme environments around hydrothermal vents at the bottom of the darkest, deepest oceans, without a single ray of sunlight. Europa's hidden ocean could offer a similar, potentially habitable environment, powered by chemistry and geothermal heat instead of sunlight. The idea that we might send a probe to drill through the ice and explore that alien sea is one of the most exciting prospects in all of science. Then there's Enceladus, a small, icy moon that has already shouted its secrets into the void. We know from the Cassini mission that Enceladus is geologically active, shooting enormous plumes of water vapor and ice crystals from a subsurface ocean out into space. These plumes are like free samples, and Cassini flew right through them, detecting organic molecules, the building blocks of life. along with salts and silica nanoparticles that suggest hydrothermal activity on the seafloor. It's essentially offering us a taste of its ocean without us even having to land. But to truly understand it, to look for signs of life directly, we need to go to the source. We need to land near those fractures known as tiger stripes and analyze that material on the surface. And we can't forget Titan, a moon so unique it feels like an entire world built from a different set of rules. It's the only moon in our solar system with a thick atmosphere, and it has a methane cycle that mirrors Earth's water cycle, with rain, rivers, lakes, and even seas of liquid hydrocarbons on its surface. The complex organic chemistry happening there under a hazy orange sky is the kind of chemistry that might have preceded life on Earth. It's a massive natural laboratory for studying the precursors to life. But Titan is also incredibly far from the Sun, and its surface is plunged in a perpetual cold twilight. This is the central paradox and the incredible challenge. These moons are so compelling precisely because of their extreme environments, but those same environments are what make them so difficult to explore. Many of these worlds are tidally locked, meaning one side is always facing their planet, creating regions of permanent shadow. Others, so far from the Sun, experience daylight as nothing more than a dim twilight, with surface temperatures hovering around -200 degrees Celsius. Landing there isn't like landing on the moon, where astronauts had a clear view of the surface. This is landing blind in unimaginable cold, on terrain we've only ever seen in low-resolution glimpses. The engineering hurdle is immense, but the potential reward is nothing less than a fundamental rewriting of biology and our understanding of life itself. This is why space agencies and private companies are pouring resources into solving the problem of dark landings, because what waits in the darkness is worth the risk. So here we are, a spacecraft on its final approach, and it's flying completely blind. This is the first and perhaps most fundamental obstacle, the utter absence of light. On Earth, or even on our moon, we take light for granted. Our eyes, our cameras, they all depend on photons bouncing off an object and traveling to a sensor. But in the perpetual night on the far side of an icy moon, there are no photons to bounce. It is a perfect, profound blackness. A standard camera, the kind we use everywhere else, would see absolutely nothing. It would be like trying to drive through a pitch-black tunnel with your headlights off. You're just hoping the road is clear. And that's a gamble you cannot take when your spacecraft is a billion-dollar, one-of-a-kind mission. This means the lander is vulnerable to a host of unseen dangers. The surface below could be a jagged nightmare of ice shards taller than buildings, formed over millennia by the intense gravitational squeezing of its parent planet. It could be hiding deep, yawning crevices that plunge into nothingness, concealed by a thin, brittle crust of frozen gas. Or it could be a treacherous, unstable slope of loose regolith, like trying to land on a giant sand dune that would cause the lander to tip over and become instantly inoperable. Without the ability to see these hazards, the mission could end in a heartbeat. This void of visual data forces a complete reimagining of perception itself. Engineers can't just make better cameras, they have to invent entirely new ways of seeing. This stands in stark contrast to how we've landed spacecraft before. Think about the Apollo missions. Those lunar landings were breathtakingly complex, but they had one enormous advantage: sunlight. The astronauts were descending onto a well-lit surface. They could look out their windows, assess the landing zone with their own eyes, and even take manual control to avoid a large crater or a field of boulders. They were an integral part of the sensing and decision-making loop. For a mission to Europa or Titan, that's impossible. Not only is there no human pilot on board, but there's also no light for them to see even if there were. This demands a level of autonomy we've never had to achieve before. The spacecraft must become its own pilot, its own navigator, and its own set of eyes, using a completely different set of senses to build a real-time map of a world we've only ever seen from a great distance. Overcoming this challenge is the critical first step, the foundation upon which every other part of the dark landing depends. It pushes innovation in two key areas: sensor fusion and artificial intelligence. The solution isn't to find one magical sensor that does everything, but to combine a suite of different technologies, each with their own strengths, and then use a powerful computer brain to merge all that data into a single, coherent understanding of the world. It's like how a bat navigates a dark cave. It doesn't use light, it uses sound. It sends out clicks and listens for the echoes, building a mental picture of its surroundings based on how those sound waves bounce back. Our landers need to do the same thing, but with a much more sophisticated toolkit. They need to create vision from nothing, constructing a reliable, three-dimensional map of the terrain in real time to guide themselves safely down. This incredible feat of engineering begins with technologies that can actively pierce through the darkness, starting with the sophisticated evolution of radar and LIDAR systems. But the total blackout is only the beginning of the nightmare. Even if we could somehow see the terrain, the environment itself is actively trying to destroy any machine we send. We are talking about cold so extreme it defies human comprehension. Temperatures on these shadowed moons don't just drop below freezing. They plunge to hundreds of degrees below zero, a level of cold where the very nature of materials begins to change. Metals that are strong and flexible on Earth become as brittle as glass. Standard lubricants freeze solid, turning gears and joints into useless blocks of ice. Even the sophisticated electronics at the heart of the lander, the very brain of the mission, are at risk of simply shutting down, their delicate circuits rendered inoperable by the intense, soul-crushing cold. Merely surviving these temperatures, let alone functioning in them, requires a complete re-engineering of almost every component, from the alloys used in the structure to the very chemistry of the batteries. And the cold is just one part of a hostile trifecta. These moons are also geologically bizarre and unpredictable. Imagine trying to land on a surface that could suddenly spew forth a plume of super-cold slush from a cryovolcano, an ice volcano that erupts water, ammonia, or methane instead of molten rock. Or consider the prospect of setting down on what appears to be solid ground, only to discover it's the frozen crust over a methane lake, a surface that could crack and give way under the lander's weight. On Titan, those dark patches seen by the Cassini probe aren't shadows. They are actual seas of liquid hydrocarbons, vast bodies of ethane and methane that could swallow a lander whole. The terrain is not just unknown, it is fundamentally alien, governed by physical and chemical processes we are only beginning to understand. Then there is the invisible killer, radiation. A moon like Europa orbits deep within Jupiter's ferocious magnetic field, a region that traps and accelerates charged particles into a relentless, deadly belt. This constant barrage of high-energy radiation can fry unprotected electronics, corrupting computer memory and degrading solar panels. It's like trying to operate a sophisticated laptop in the heart of a nuclear reactor. Shielding against this requires heavy materials like lead or tungsten, but every extra gram of weight on a spacecraft is precious and astronomically expensive to launch. Engineers are trapped in a constant battle, forced to design lightweight yet incredibly effective radiation hardening for every microchip and sensor, or find clever ways to hide sensitive components behind other structures for protection. This means the design of a lander for such a mission is a masterpiece of defensive engineering. It's not just about building a machine that works. It's about building a machine that can withstand an endless, multi-front assault from the environment. Thermal management systems, using a combination of heated components and incredibly efficient insulation, must maintain a tiny, warm island of functionality inside a shell of deep space cold. Exposed materials must be chosen not just for strength, but for their resistance to corrosion from exotic chemicals like methane or ammonia. Every system, from the primary to the backup, must be designed with this harsh reality in mind, often for missions that are meant to last not just days but years. This incredible durability is the only thing that will allow us to unlock the scientific secrets hidden in these extreme worlds, and it all depends on one critical resource: a constant, reliable source of power to sustain this life support system for machines. Now, let's add another layer to this already immense challenge: the tyranny of distance. Even if we build a lander tough enough to survive the cold and smart enough to see in the dark, we face a problem that no amount of engineering can overcome: the fundamental speed limit of the universe. A radio signal traveling at the speed of light is incredibly fast, but the gulfs between planets are so vast that it becomes achingly slow. We are not just talking about a bad phone connection. We are talking about a complete and utter disconnect from our spacecraft during the most critical moments of its existence. Consider a mission to Enceladus, that icy moon of Saturn shooting geysers into space. When Earth and Saturn are at their closest, a one-way radio signal still takes over an hour and 20 minutes to make the journey. But planets move, and at their farthest, that delay can stretch to well over 2 hours. This means a simple hello from the spacecraft and the "we read you" response from Earth would take more than 3 hours to complete a single exchange. Now imagine that spacecraft is in the final 15 minutes of its descent. It suddenly detects a giant, unseen crevasse directly in its path. It has mere seconds to fire its thrusters and move to a new landing site. If it had to call home for instructions, by the time its desperate message reached Earth and our "abort, abort" command traveled all the way back, the lander would have been a silent, shattered wreck at the bottom of that crevasse for over 2 hours. Real-time control is not just difficult, it is physically impossible. This colossal communication delay forces a monumental shift in philosophy. We cannot pilot these spacecraft. We cannot be their conscious mind making split-second decisions from a control room on Earth. Instead, we must build them to be their own pilots. We have to give them a brain, an artificial intelligence capable of sensing, understanding, and reacting to its environment entirely on its own. This is the essence of autonomy. It's not just a fancy feature, it is an absolute necessity for survival. The spacecraft must become a thinking, decision-making entity. During the final descent, it will be utterly alone, relying on its own wits to navigate a world we have never touched. This level of intelligence requires staggering computational power. The lander's brain must be able to take in the flood of data from its radar, LIDAR, and thermal sensors, instantly fuse it all into a coherent, three-dimensional map of the terrain below, and then compare that map against a vast library of known hazards. Is that a safe, flat plane or a deceptive soft patch? Is that dark area a shadow or a bottomless pit? It must calculate a new trajectory in milliseconds, commanding its thrusters to fire with precise timing to avoid catastrophe, all while managing its rapidly diminishing fuel supply. And it must do this not once but continuously, every second of the way down, adapting to surprises we could never have predicted from millions of miles away. Building this fail-safe system is one of the most complex tasks in all of engineering. It's a deep integration of cutting-edge robotics, sophisticated machine learning algorithms, and redundant systems engineering. The algorithms themselves are trained for years on supercomputers, running through millions of simulated landing scenarios on virtual alien worlds. They are taught to recognize every conceivable type of danger, from jagged ice ridges to deceptive snowy slopes. And crucially, they are built with layers of redundancy. If the primary computer freezes in the extreme cold, a backup must instantly take over without a single missed calculation. This isn't about building a smart machine, it's about building a trustworthy one, an automated explorer that we can send into the ultimate unknown with the confidence that it can handle anything it finds. This incredible capability hinges on one technology above all others: the artificial intelligence that serves as the lander's mind and eyes. So at the very heart of this autonomous explorer, making life or death decisions millions of miles from home, is its artificial intelligence. This isn't the kind of AI you might see in movies, a conscious entity pondering its existence. This is a hyper-specialized, incredibly powerful computational brain, and its sole purpose is to process a fire hose of sensory data and translate it into a single, critical action: a safe landing. Think of it as the world's most attentive and lightning-fast pilot, one that can assess a completely alien landscape in the blink of an eye and react without a single moment of hesitation. It takes the raw, often confusing information from its radar, LIDAR, and thermal sensors and fuses it all into a dynamic, three-dimensional map of the world below. This map isn't just a picture, it's a living, breathing model that classifies every meter of terrain. It identifies a safe, flat area as a potential landing zone, flags a jagged outcrop as a catastrophic hazard, and marks a softly undulating dune as a potential risk. And it does this continuously, updating its understanding dozens of times per second as the lander descends, constantly recalculating its trajectory to steer toward the safest possible spot. The magic behind this capability is machine learning. Before this AI ever left Earth, it went to school for years, not in a classroom, but inside powerful supercomputers. Engineers fed its algorithms millions upon millions of simulated landing scenarios. It practiced on virtual versions of Europa's chaotic ice ridges, Titan's methane-soaked dunes, and the rocky, unpredictable surfaces of asteroids. It learned to recognize the subtle sensor signatures of a hidden crevasse disguised by a thin layer of frost, or the way a certain slope angle could cause a lander to tip over upon touchdown. This extensive training is what allows it to adapt to the truly unexpected. It isn't just following a pre-programmed checklist. It's using its accumulated experience to make judgment calls in situations its human creators may never have even imagined. A prime example of this technology in action is NASA's Autonomous Landing Hazard Avoidance Technology, or a LHAT. This system uses a sophisticated LIDAR to create extremely high-resolution maps of the terrain during descent. Its AI brain is trained to analyze that map in real time, identifying hazards like large rocks or steep slopes that are too dangerous for touchdown. It then compares every possible landing point within its reach against a strict set of safety criteria, scoring them and commanding the vehicle to divert to the best available option. Originally developed for lunar missions where long shadows can create their own kind of darkness, a LHAT is a proving ground for the very AI principles that will be essential for landings in total blackout. It demonstrates that we can trust a machine to see what we cannot and make a safe choice where no human intervention is possible. This intelligence transforms the lander from a passive, pre-programmed robot into an active, discerning explorer, capable of handling the infinite unpredictability of an alien moon. But even the most brilliant brain needs accurate and comprehensive information to work with, which is why the raw data from individual sensors must be blended together into a single, perfect picture. But even the most advanced artificial intelligence would be useless without accurate and timely information. It's one thing to have a brilliant pilot. It's another thing entirely to give that pilot clear, reliable eyes and ears. And in the profound darkness of an alien moon, no single type of sensor can provide the complete picture. Each one has its own strengths and its own blind spots. Radar can see through obscuring haze but might miss fine details. LIDAR creates exquisitely detailed maps but can be thrown off by certain types of dust or ice. An infrared camera can detect warmth but might misinterpret a cold, flat plane. Relying on just one would be like trying to navigate a complex world using only your sense of smell. You'd get some information, but you'd miss crucial context and make catastrophic mistakes. The solution, the only way to achieve true perception in the void, is a sophisticated process called sensor fusion. This is the technological symphony that allows the lander to construct a single, trustworthy reality from a chorus of different data streams. Sensor fusion works exactly as it sounds. It fuses or blends together the information from a suite of different sensors. Think of it like how your own brain operates. You don't rely solely on your eyes to cross a busy street. You also use your ears to listen for approaching cars and your sense of touch to feel the curb beneath your feet. Your brain seamlessly combines all these inputs to create a comprehensive understanding of your environment and keep you safe. A dark landing spacecraft does the same thing, but its senses are far more exotic. It uses radar, which sends out radio waves and listens for their echo to measure the distance to the ground and its velocity relative to the surface. This is incredibly effective at piercing through total darkness, dust storms, or thick atmospheric haze, providing robust, reliable data about the big picture. At the same time, its LIDAR system is firing millions of pulses of laser light every second. Each pulse that reflects back is meticulously timed, building up a point-by-point, incredibly high-resolution, three-dimensional map of the terrain below. This is what can reveal the individual boulders, the subtle slopes, and the tiny cracks that radar might gloss over. Meanwhile, infrared and thermal cameras are scanning the area, not for visible light but for heat. They detect the faint thermal signatures of different materials, perhaps spotting a region of warmer, thinner ice that might be unstable or a cold, solid rock field that would make for a perfect landing site. These cameras can also analyze the composition of the surface, identifying whether it's water ice, solid rock, or organic material. And underpinning all of this is the Inertial Measurement Unit, or IMU. This is the lander's internal sense of balance and movement. Using a combination of gyroscopes and accelerometers, it constantly tracks every tiny change in the spacecraft's orientation, rotation, and acceleration. If the radar says you're descending at 10 meters per second, but the IMU feels a sudden lurch to the side, it helps the computer understand that you might be caught in a crosswind or that your thruster fired incorrectly. It's the ultimate reality check for all the other external sensors. The real magic happens in the onboard computer, where powerful algorithms weigh, compare, and merge all these simultaneous data streams. The system is smart enough to know that LIDAR data is more precise for mapping tiny features, but that radar is more trustworthy for overall velocity. It can identify when one sensor might be giving a faulty reading. Perhaps a patch of highly reflective ice is confusing the LIDAR and automatically discount that input in favor of the others. By cross-referencing every piece of information, it cancels out the weaknesses of each individual technology and amplifies their collective strengths. The final product is a dynamic, living, three-dimensional map that is far more accurate and reliable than anything any single sensor could ever produce. This fused reality is what the AI pilot uses to make its split-second decisions, allowing it to confidently navigate a world it has never seen with a clarity that would be impossible any other way. This multi-sensory approach is the golden key to touching down safely on uncharted, lightless terrain, and it all begins with the most stalwart and reliable of these sensors, radar. At the core of this multi-sensory navigation system is one of the oldest and most trusted technologies for seeing the unseen, radar. But the radar systems being developed for these missions are a far cry from the simple blips on a screen used to track airplanes or predict weather. This is radar pushed to its absolute limits, refined and reimagined for the most extreme environment imaginable. The fundamental principle remains the same. The spacecraft sends out a burst of radio waves, and then it listens carefully for the faint echo as those waves bounce back from the surface below. By precisely timing how long it takes for that echo to return, the radar can calculate the exact distance to the ground. This simple measurement is the bedrock of the entire landing sequence, providing the constant, reliable altitude data that tells the lander just how far it has left to fall. But modern space radar goes so much further than just measuring distance. One of the most powerful advancements is a technology called synthetic aperture radar, or SAR. The word synthetic here is key. Instead of relying on a single, large, and physically impractical antenna to get a high-resolution image, SAR uses the motion of the spacecraft itself to synthetically create a massive antenna. As the lander moves along its descent path, it takes multiple radar readings of the same spot on the ground from slightly different positions. A powerful onboard computer then combines all these individual readings, effectively stitching them together to create an image with a resolution that would normally require an antenna the size of a football field. This allows SAR to see through total darkness, thick atmospheric haze, and even penetrate the first few meters of surface material. It can reveal the hidden structure of the ground below, identifying buried crevices, layers of different ices, or pockets of unstable, porous regolith that would collapse under a lander's weight. It's like giving the spacecraft a pair of X-ray glasses to see the dangers lurking just beneath the surface. Working in perfect harmony with this imaging radar is another critical type, Doppler radar. While SAR is busy building a detailed picture of the ground, Doppler radar is focused on one thing and one thing only: motion. It exploits a fundamental principle of physics known as the Doppler effect, the same phenomenon that makes a siren's pitch sound higher as an ambulance races toward you and lower as it speeds away. The radar transmits a signal at a specific frequency, and when that signal bounces off the moving surface and returns, its frequency has shifted. By meticulously measuring that tiny shift in frequency, the Doppler radar can calculate the lander's velocity relative to the ground with breathtaking accuracy. It can tell if the spacecraft is descending at 2.1 meters per second or 2.2. This is not just helpful data, it is absolutely critical for controlling the descent. The lander's computer uses this real-time velocity reading to make constant, microscopic adjustments to its thrusters, ensuring a controlled, gentle touchdown rather than a catastrophic crash. The challenge isn't just making these radars powerful and accurate, it's making them tough enough to survive the journey. The electronics inside must be radiation-hardened to resist the constant bombardment of high-energy particles that would quickly fry ordinary circuits. They have to be miniaturized to save every possible gram of weight, yet still powerful enough to punch their signals through unknown atmospheres and ice. They must operate flawlessly in a vacuum while enduring temperature swings of hundreds of degrees. A fantastic real-world example of this technology in action is on the European Space Agency's JUICE mission to Jupiter's icy moons. While JUICE is an orbiter and not a lander, its advanced ice-penetrating radar is designed to do exactly what a future lander's system would need to do: map the subsurface structure of moons like Ganymede and Callisto from orbit, searching for that hidden liquid water. It's a crucial proving ground for the radar technology that will one day guide a lander to a safe spot on the surface. This incredible technology transforms the landing sequence from a hopeful gamble into a precise, data-driven operation. The fusion of SRR's detailed imaging and Doppler's pinpoint velocity measurements allows the lander to not just know where the ground is, but to understand it intimately and approach it with perfect control. It can identify a seemingly perfect landing zone, then use its penetrating vision to discover a fragile crust of ice over a void and immediately divert to a safer target. Radar provides the robust, reliable backbone of perception in the darkness, a trusted guide that works in any condition. But while radar gives us the big picture and the crucial velocity data, it's another technology that provides the exquisitely fine detail, painting the world below with a brush of pure laser light. While radar provides the robust, long-range view, LIDAR is the master of exquisite, high-resolution detail. Think of it as the ultimate precision artist of the sensor suite. The principle is elegantly simple, yet the execution is breathtakingly complex. The system fires millions of tiny, precisely targeted pulses of laser light toward the ground every single second. Each photon races toward the surface, hits its target, and a small fraction of them make the return journey back to a sensitive detector on the lander. By meticulously timing how long this round trip takes for each and every pulse, and because we know the exact speed of light, the onboard computer can calculate the distance to that specific point with an accuracy down to just a few centimeters. It's like the spacecraft is spray painting the entire landing zone with an invisible grid of light, measuring the exact height of every single point it touches. As the lander descends, it continues this furious barrage of laser pulses, and with each passing millisecond, it gathers more and more of these individual data points. Gradually, a breathtakingly detailed three-dimensional map begins to materialize inside the computer. This isn't a flat photograph, it's a rich, depth-filled point cloud where every single dot has a precise location in space. This digital terrain model can reveal a boulder the size of a bowling ball, a crack in the ice just a hand's width across, or a slope so subtle it would be invisible to any other sensor. This incredible resolution is what makes LIDAR absolutely indispensable for the final moments of descent, where spotting that one last, unseen hazard can mean the difference between a perfect landing and a mission-ending impact. Of course, building a LIDAR system for a deep space mission is a monumental engineering challenge. It has to be incredibly lightweight because every gram launched into space costs a fortune. It must be incredibly energy efficient, as power is a precious commodity in these dark, sunless realms. And perhaps most critically, it has to be built to survive an environment that would instantly destroy any consumer gadget. The lasers, the mirrors, the detectors, all of it must be hardened to withstand the brutal shaking of launch, the crushing vacuum of space, and temperature swings that would shatter ordinary glass and warp common metals. These are not off-the-shelf components. They are custom-built marvels of miniaturization and durability, designed to operate flawlessly in conditions that push the very limits of material science. We already have a fantastic proof of concept working millions of miles away on Mars. The Perseverance rover uses a LIDAR system called SuperCam not just for navigation, but for its scientific mission. It can zap a rock from over 20 feet away and, by analyzing the faint spark of plasma created, determine that rock's chemical composition. This same core technology is being radically adapted for the unique challenges of darker moons. Engineers are experimenting with different laser wavelengths, specifically choosing colors of light that are better at penetrating the kinds of fine, icy dust that might be kicked up by descent thrusters or that naturally hangs in the thin atmospheres of worlds like Titan. They are also developing more advanced noise filtering algorithms, allowing the system to ignore the visual noise and still lock onto the true signal of the solid ground below, even in a blizzard of swirling frozen particles. This powerful combination of technologies, radar for the big picture and robust velocity data, and LIDAR for the microscopic, high-resolution detail, creates an almost god-like view of the landing zone for the AI pilot. But to truly understand the nature of the ground it's about to touch, the lander needs one more sense, one that doesn't just see the shape of the world, but can also feel its temperature and composition. This is where infrared and thermal imaging add a crucial final layer of perception, revealing the hidden properties of the alien landscape. So while LIDAR maps the physical shape of the terrain with laser precision, it can't tell us anything about what that terrain is actually made of or its hidden thermal properties. This is where infrared and thermal imaging step in to complete the picture, adding a completely new dimension to the lander's perception. These cameras operate on a fascinatingly simple principle. All objects, no matter how cold, emit a faint signature of thermal radiation. It's a fundamental law of physics. The lander's infrared sensors are designed to be exquisitely sensitive to these tiny differences in heat, effectively allowing the spacecraft to see the world not by the light that bounces off it, but by the warmth, or lack thereof, that it naturally gives off. In the perpetual, deep freeze darkness of an alien moon, this ability to visualize heat is like having a superpower. Consider the surface of Europa. To a visible light camera, a vast, flat plain of ice might look like the perfect, smooth landing site. But an infrared camera could reveal that same plain as a patchwork of different temperatures. Some areas might appear slightly warmer than their surroundings. This subtle thermal signature could be a critical warning, a sign of thinner ice, perhaps warmed from below by the ocean's proximity, making it dangerously fragile and likely to crack under the weight of a lander. Another warmer spot might indicate a recent eruption from a volcano, where slushy, slightly warmer water has oozed out onto the surface and frozen into an unstable, unpredictable terrain. The infrared camera transforms the landing site from a simple monochrome map into a detailed thermal diagram, highlighting potential hazards that are completely invisible to any other sensor. It turns a hidden weakness into a visible warning. This technology is rarely used alone. It's almost always paired with another incredible instrument, a spectrometer. While the infrared camera is busy mapping the broad temperature variations, the spectrometer performs a kind of chemical autopsy on the same light. Every element and compound absorbs and emits infrared radiation in its own unique signature way, like a microscopic fingerprint. By analyzing the specific wavelengths of infrared light coming from a target, the spectrometer can determine its composition from a distance. Is that dark patch a field of bare, solid rock? Is it a layer of complex organic molecules, the building blocks of life, or is it just a different type of ice? This combination is devastatingly effective. The camera says that spot is warmer and could be dangerous, and the spectrometer immediately adds, and it's warmer because it's a layer of ammonia-rich ice, which has a lower melting point. This gives the AI pilot not just a map of where to avoid, but a scientific understanding of why. Building cameras this sensitive for space is a feat of engineering in itself. The biggest enemy of a good thermal image is heat, not from the environment, but from the camera's own electronics. To detect the incredibly faint heat signatures from a distant, frozen moon, the sensor itself must be cooled to temperatures even colder than the environment it's trying to observe. This is often achieved with tiny, highly efficient cryogenic coolers that use compressed gases or advanced thermoelectric materials to siphon away every bit of waste heat, allowing the detector to focus solely on the subtle whispers of infrared light from the world below. Recent advances have made these coolers smaller, more reliable, and far less power-hungry, which is absolutely critical for a mission where every watt of power is a precious resource. This allows for a new generation of space-rated infrared imagers that are more sensitive, have higher resolution, and can operate for years on end without degradation. This thermal and chemical vision forms the final, crucial layer in the lander's sensory suite. Radar provides the robust, all-weather data on distance and velocity. LIDAR paints the exquisitely detailed three-dimensional map of the terrain's shape, and infrared imaging reveals the hidden nature of that terrain itself, its temperature, its stability, and its very composition. Fused together by the AI, these datasets create a holistic, multi-dimensional understanding of the landing site that is far greater than the sum of its parts. It is the closest thing we have to giving a machine human-like perception, allowing it to assess a completely alien landscape with a depth of understanding that ensures not just a safe landing, but a scientifically valuable one. Yet even with this near-perfect view of the external world, the lander still needs an unshakable sense of its own internal state and motion, a foundation that remains steady even when all external references temporarily vanish. Now, with all these incredible external sensors building a rich picture of the world outside, it's easy to forget that the lander also needs an unshakable sense of itself, an internal compass that never loses its way, even when the outside view gets blurry or disappears completely. This is the domain of the Inertial Navigation System, or INS, and it serves as the spacecraft's fundamental sense of balance and motion. While radar and LIDAR are looking outward, the INS is looking inward, providing a constant, reliable stream of data about the lander's own position, orientation, and velocity that is completely independent of any external reference. It is the ultimate self-reliant navigator. The core of any INS is a deceptively simple set of instruments, accelerometers and gyroscopes. An accelerometer does exactly what its name implies. It measures acceleration, every tiny change in the lander's speed or direction. A gyroscope, on the other hand, measures rotation and orientation. It knows if the spacecraft is tilting, rolling, or yawing. The magic is in the mathematics. The system knows its exact starting point, the position and velocity it had when it was released from its orbiter. From that single moment onward, the INS continuously integrates all the data from its accelerometers and gyroscopes. It takes every minuscule measurement of acceleration and rotation, and through a process called dead reckoning, calculates how its position has changed from that initial point. It's like being blindfolded in the back of a car and being able to draw a perfect map of the entire journey just by feeling every turn, every stop, and every acceleration. This allows the INS to always know, to a remarkably precise degree, exactly where it is and how it's moving through space. This capability becomes absolutely critical during the most dynamic and dangerous part of the mission, the final descent. As the lander fires its thrusters to slow down, to change direction, or to avoid a last-minute hazard, its external sensors can be temporarily blinded. The firing thrusters themselves can kick up a cloud of dust and ice particles that might confuse LIDAR or create plasma that interferes with radar. For those few crucial seconds, the spacecraft might be flying partially blind on the outside. But on the inside, the INS never blinks. It feels every pulse from the thrusters, every tiny gust of wind in a thin atmosphere, every slight rotation. It provides the stable, uncontaminated data stream that the flight computer uses to ensure the lander doesn't go spinning off course during these critical moments. It is the anchor that holds fast while the storm of sensory input rages around it. Of course, this internal sense is not perfect. The tiny errors in the accelerometers and gyroscopes, errors smaller than the width of an atom, accumulate over time. This phenomenon, called drift, means that an INS that isn't periodically corrected by an external reference like a star tracker or a GPS signal will slowly but surely become less accurate. For a mission to an alien moon, this presents a huge challenge. There is no GPS constellation around Europa. A star tracker, which uses pictures of the stars to orient itself, might be useless if the lander is constantly rotating during its descent or if dust is obscuring its lens. This means the INS for a dark landing must be engineered to a level of perfection we rarely see. The gyroscopes and accelerometers must be incredibly precise, sensitive enough to detect a change in velocity of a fraction of a millimeter per second, yet robust enough to survive the violent shaking of launch and the extreme temperature swings of deep space. They are often housed in super-stable, temperature-controlled enclosures and built with redundant sets of sensors that constantly cross-check each other to identify and correct for any tiny errors before they can accumulate into a dangerous miscalculation. The technology making this possible is advancing at a breathtaking pace, largely driven by innovations in micro-electromechanical systems, or MEMS. This is the technology that puts tiny mechanical elements, like miniature gyroscopes and accelerometers, onto a single silicon chip, similar to how we make computer processors. The gyroscope in your smartphone that knows when you rotate the screen is a MEMS device. For space missions, engineers are taking this same core concept and hardening it to an incredible degree, creating MEMS-based INS units that are smaller than a deck of cards, use a fraction of the power of older systems, and are just as accurate. This miniaturization is a game-changer, allowing landers to carry multiple, redundant INS units without adding significant weight or draining precious power, creating a network of internal guidance that is both incredibly smart and incredibly resilient. So as the lander makes its final approach, it's this perfect partnership between external and internal sensing that creates true navigational confidence. The radar, LIDAR, and infrared cameras build a detailed map of the external world, while the inertial navigation system maintains an unwavering record of the lander's own journey through that world. The flight computer fuses these two streams of data together, using each to check and correct the other. If the INS senses a movement that the external cameras don't confirm, it might indicate one of the sensors is getting faulty data. If the LIDAR shows a sudden change in altitude that the INS didn't feel, it might mean the ground itself is unstable. This continuous crosstalk creates a rock-solid, real-time understanding of both the vehicle and its environment, providing the flawless situational awareness needed to make the final, most important decisions of the mission. Gathering all this sensory data is only half the battle. The true test comes in the final, heart-pounding moments of descent when the lander's brain must process that information and make life or death decisions in the blink of an eye. This is the domain of hazard detection and avoidance, a system that acts as the spacecraft's final line of defense against the unseen dangers of an alien world. It's not enough to simply map the terrain. The lander must be able to interpret that map instantly, identify a threat the size of a dining room table, and execute a brand new landing plan, all while plummeting toward the surface at dozens of meters per second and with a rapidly diminishing fuel supply. This isn't a pre-programmed sequence. It's a dynamic, real-time conversation between the sensors, the AI, and the thrusters, a high-stakes dance where a single misstep means catastrophe. The algorithms driving this system are designed with one overriding principle: safety first, precision second. A mission can still be a spectacular success if it lands a few hundred meters from the ideal, scientifically perfect target site. But a mission is an absolute failure if it lands directly on a sharp spire of ice and is torn apart on impact. The software is therefore built to be inherently conservative, constantly running through a checklist of safety criteria for every square meter of ground within its reach. It's looking for a combination of factors: a slope shallow enough that the lander won't tip over, a surface hard enough to provide stable support, and an area clear of large obstacles that could damage the landing legs or instruments. It assigns every potential landing spot a constantly updating safety score. If the primary target suddenly drops below a certain threshold, perhaps because the LIDAR just revealed a previously hidden boulder field, the system doesn't hesitate. It immediately triggers an avoidance maneuver, commanding the thrusters to fire and push the lander toward the next best option, even if that burn uses precious fuel that was reserved for the final, gentle touchdown. This process involves incredibly sophisticated trade-offs, a kind of high-speed calculus of risk conducted entirely by machine. Imagine a simulated landing on Titan. The lander's radar identifies a broad, flat plain that looks perfect, but its infrared sensor reveals the area is anomalously warm, suggesting a possible slushy instability just beneath a thin crust. Meanwhile, its LIDAR has mapped a second site a kilometer away. This alternate spot is on a slight slope, which is not ideal, but the composition appears to be solid, stable water ice. The hazard detection system must now weigh these two imperfect options in milliseconds. Does it risk the seemingly flat but potentially mushy terrain, or does it commit to a slope that will cause the lander to tilt but likely remain intact? It makes this choice based on a hierarchy of risks programmed by its engineers back on Earth, choosing the option that offers the highest probability of survival, even if it's not the most scientifically elegant landing. To ensure these systems can handle the infinite unpredictability of a real mission, they are put through hell on Earth long before they ever see space. Engineers test them in analog environments, places that are the closest we can get to an alien moon without leaving our planet. Rovers equipped with prototype hazard detection systems are driven across the jagged, volcanic rock fields of Hawaii, which mimic the rugged terrain of Mars. They are tested in the perpetual darkness and crushing cold of polar ice caps during the long winter, where they must navigate crevasse fields and soft snowdrifts using only their onboard sensors, just as they would on Europa. These grueling field trials are invaluable, revealing flaws and edge cases that no number of computer simulations could ever predict, like how a specific type of ice can perfectly mimic the radar signature of solid ground, or how blowing dust can temporarily blind a LIDAR unit. Each failure in testing is a lesson learned, a software patch written, and a step toward a system that can be trusted with a billion-dollar mission and humanity's hopes for discovery. This relentless, proactive approach to identifying and evading danger is what transforms a controlled crash into a controlled landing, and it all depends on a constant, unwavering source of energy to power this incredibly demanding final act. Yet for all this incredible technology to function, from the brilliant AI brain to the suite of advanced sensors, it all hinges on one absolutely critical resource: a constant, reliable, and robust supply of electrical power. Imagine the lander as a master surgeon performing the most delicate operation imaginable, but instead of being in a brightly lit hospital, it's in the middle of a wilderness with no access to electricity. Its tools, its lights, its monitoring equipment, everything would be useless. In the profound and perpetual darkness of an alien moon, this is the fundamental challenge. There is no sunlight to capture with solar panels. The lander is utterly alone, and it must carry its own entire power plant with it, a system that can generate enough electricity to sustain its demanding operations, not just for the few hours of descent, but potentially for years of scientific discovery on the surface. The historical and most trusted solution to this problem is a remarkable piece of technology called a radioisotope thermoelectric generator, or RTG. The principle is elegantly straightforward, born from the natural process of radioactive decay. Inside the RTG is a pellet of a radioactive material, typically plutonium-238. This isotope is not used for a chain reaction like in a nuclear bomb or reactor. Instead, it naturally and continuously decays, releasing a steady stream of heat as it does so. This isn't a violent, explosive heat, but a predictable, relentless warmth that can last for decades. Wrapped around this heat source are devices called thermocouples, which are essentially magic tricks of material science. A thermocouple is made from two different types of metal joined together. When one side is heated and the other side is kept cool, a voltage is created across the junction, directly converting heat into electricity. The RTG uses the radioactive decay for the heat and the cold vacuum of space as its cooler, creating a simple, solid-state generator with no moving parts to wear out or break. The track record of RTGs is a testament to their brilliance. They are the unsung heroes of deep space exploration. The Voyager probes, now in interstellar space, are still powered by the same RTGs launched in the 1970s. The Curiosity and Perseverance rovers on Mars use them to heat their electronics and power their instruments through the frigid Martian nights and dust-laden winters. For a dark moon landing, an RTG provides the perfect baseline, a constant, dependable hum of power that you can set your watch to, completely immune to whether it's day or night, or if dust has covered your panels. It is the ultimate reliable companion. However, RTGs are not perfectly efficient. They convert only a small fraction of the available heat into usable electricity, wasting the rest. For missions that might need more power, perhaps to run a powerful drill to bore through ice or to operate a complex chemistry lab, engineers are turning to a more advanced cousin, the Stirling radioisotope generator. This system still uses the same reliable radioactive heat source, but instead of thermocouples, it uses the heat to drive a piston in a Stirling engine. The expanding and contracting gas in the engine drives the piston, which turns a generator, creating electricity. This mechanical process is significantly more efficient than thermoelectrics, meaning you can get the same amount of power from less plutonium or more power from the same amount. This is a crucial advancement, as plutonium-238 is extremely rare and difficult to produce. While more complex due to its moving parts, advanced Stirling systems represent the next evolutionary step in nuclear batteries for space. Looking even further into the future, for truly power-hungry missions like a potential future base on a dark moon, concepts for compact fission reactors are on the drawing board. These would work on a principle closer to a miniature nuclear power plant, using a controlled chain reaction to generate vastly more power than an RTG ever could. This could enable missions we can only dream of today, like melting probes that tunnel down through miles of ice to reach the hidden ocean of Europa, or large-scale facilities that process local resources. For shorter duration missions, advanced fuel cells, which create electricity through a chemical reaction between stored fuels, are also a viable option, offering high power density for intense periods of activity. This relentless pursuit of reliable power is what turns a mission from a fleeting visit into a sustained presence. It is the lifeline that keeps the lander's brain active, its senses sharp, and its voice strong enough to call home across the incredible void. It ensures that after the intense drama of the landing is over, the lander doesn't simply fall silent and freeze in the dark, but can wake up, extend its instruments, and begin its true purpose, unlocking the secrets of an alien world. And to share those secrets with those of us waiting eagerly back on Earth, it needs to find a way to speak to us. But even with a reliable power source humming away, the lander faces another immense challenge: the sheer difficulty of having a conversation across the solar system. Imagine trying to send a text message with a weak cell signal that takes hours to deliver, and if even one letter gets lost in transmission, the entire message becomes gibberish. Now imagine that signal has to travel billions of miles through the empty, interference-filled void of space. This is the monumental task of deep space communication, and for a lander on a dark, distant moon, it requires a suite of clever strategies just to whisper its findings back home. The primary tool for this conversation is a high-gain antenna, a sophisticated dish carefully pointed toward Earth. High-gain means it focuses its radio signal into an incredibly narrow, powerful beam, like using a laser pointer instead of a floodlight. This is essential because over such vast distances, the signal weakens to an almost unimaginably faint whisper by the time it reaches our receivers. To put this into perspective, the signal strength from a spacecraft at Pluto is over 1 million times weaker than the signal from a typical GPS satellite orbiting Earth. Catching that signal requires an enormous amount of patience and some of the most sensitive listening equipment ever built, like NASA's Deep Space Network, a globe-spanning array of gigantic radio telescopes dedicated solely to listening to our robotic explorers. Because this connection is so fragile and delayed, the lander cannot simply stream its data live. It must become its own archivist, storing every precious byte of information, every image, every sensor reading, every scientific measurement, on robust, radiation-hardened solid-state drives. It patiently collects this treasure trove of data for days or even weeks, waiting for the perfect moment to transmit. Consider a lander on Pluto's moon Charon. Earth and Charon are only in a favorable position for communication for certain periods, dictated by their orbital dance and the rotation of the planets. The lander might have to store months of discoveries before it even gets a chance to phone home. To make the most of these brief communication windows, engineers use sophisticated data compression algorithms, not unlike zipping a large computer file, to shrink the data down and send the most critical information first, ensuring that even if the connection is lost, the most valuable insights are not. To improve the odds of a successful call, missions often rely on a celestial relay race. Instead of trying to talk directly to Earth, which might be below the horizon or blocked by terrain, the lander can beam its data up to an orbiter flying overhead. This orbiter, with its larger power supply and bigger antenna, acts as a communications middleman, storing the lander's data and then later transmitting it at a much higher rate back to Earth when the alignment is perfect. This concept of a network using multiple orbiters or even future spacecraft at Lagrange point is the foundation of an emerging interplanetary internet. These protocols allow for a store and forward model of communication, where data hops from one node to another across the solar system, ensuring it eventually finds its way home, even if the direct path is blocked. Despite all this planning, blackout periods are inevitable. During critical maneuvers like landing, when the lander is rotating or its antenna is not perfectly pointed, communication will be lost. This is why the entire mission is designed around asynchronous communication. Engineers on Earth send up a detailed set of instructions, a script for the lander to follow. The lander then executes that script autonomously, storing all the results. Only later, when it re-establishes a stable link, does it send back a comprehensive report of everything it did and everything it found. This requires an incredible level of trust in the lander's autonomy and a robust design that ensures not a single bit of data is lost to the cold of space. It's a painstaking, patient process of cosmic communication, where every successful data packet received is a monumental achievement, and ensuring that the lander is intact and stable enough to send that data begins the moment it makes contact with the surface. After all the incredible technology that guides the lander safely through the darkness, the AI brain, the suite of advanced sensors, the robust power and communication systems, the entire mission ultimately comes down to one single critical moment, the moment of contact. All that effort, all that innovation converges on the final inch of descent. This is where the landing gear takes center stage, transforming a controlled descent into a stable and survivable touchdown. But this is no simple set of legs. It is the lander's first and only physical interaction with an entirely unknown world, and it must be designed to handle absolutely anything it might encounter. We are talking about a system that must be both incredibly strong and astonishingly delicate, a masterpiece of mechanical adaptability. The range of possible surfaces is almost unimaginable. The lander could be setting down on a plane of rock-hard water ice, smooth as a skating rink and just as slippery. It could be touching a surface of loose, fluffy regolith that behaves like fine, dry snow, offering no support and threatening to swallow the vehicle whole. Or it could be a bizarre combination of both a brittle crust of ice over a bottomless powder, like the dreaded sugar snow that traps Arctic explorers. The landing gear has to be versatile enough to succeed on all of them. To achieve this, engineers incorporate several key features. First, the legs themselves are made from advanced, shock-absorbing materials like composite honeycomb structures or specialized alloys that can crumple in a controlled way, dissipating the energy of impact instead of transferring it to the fragile instruments housed in the main body of the lander. But passive absorption is only the start. The most advanced designs include active systems. Some concepts feature legs with deployable pads or footings that can change their shape or size upon contact. Imagine a foot that senses it starting to sink into a soft surface. It might instantly deploy a wider, snowshoe-like plate to distribute the lander's weight and prevent it from burying itself. Conversely, if it touches down on a hard, slick slope, sharp spikes or claws might extend from the footpads to dig into the ice and prevent any dangerous sliding. The most futuristic concepts involve fully robotic legs, inspired by the walking robots we see here on Earth. These legs wouldn't just be static struts, they would have articulated joints powered by tiny motors. Using data from the terrain sensors right up to the last second, these legs could actively adjust their posture and length during touchdown, much like a person stepping onto an unstable boat might bend their knees to maintain balance. One leg might extend slightly to compensate for a rock, while another retracts to find a firmer footing, ensuring the main body of the lander stays perfectly level. Consider the challenges of a moon like Iapetus with its famous two-tone coloration and wildly varied terrain. One region might be dark as coal and covered in loose, rocky debris, while another is bright white and composed of pristine, hard ice. A lander there would need landing gear that could confidently handle both extremes within a single mission. This level of adaptability isn't just theoretical. It is rigorously tested in some of the most extreme environments on our own planet. Engineers take prototype landers to the soft, shifting dunes of deserts to simulate loose regolith. They go to the hard, wind-swept ice sheets of Antarctica or the volcanic rock fields of Iceland to stand in for the frozen, rugged surfaces of distant moons. In these analog environments, they can repeatedly drop, tip, and stress the landing systems, gathering priceless data on how the mechanisms perform under real-world pressure. This physical testing is the crucial final validation that complements all the computer simulations and sensory wizardry, proving that the hardware can actually deliver on the promise of a soft landing. This relentless pursuit of mechanical perfection on the ground ensures the lander survives its first handshake with an alien world, ready to then unlock its secrets. Before a single component ever leaves the laboratory, it must first survive a brutal gauntlet of simulated nightmares, a digital proving ground where engineers can conjure every conceivable disaster in the safety of a virtual world. This process begins with hyper-realistic computer simulations, where every variable of the alien environment is modeled with painstaking accuracy. Powerful supercomputers run thousands of landing scenarios in fast-forward, each one slightly different from the last. The virtual gravity of Europa, a mere 13% of Earth's, is applied to the digital lander's physics model. The non-existent atmospheric drag of a vacuum or the subtle, soup-like resistance of Titan's thick nitrogen haze is factored into the descent equations. The algorithms are tested against every imaginable surface composition, from jagged, fractured ice that could shred landing legs to fields of fluffy, carbonaceous snow that offer no support. These simulations are designed specifically to break things. Engineers intentionally introduce catastrophic failures to test the system's resilience. What happens if a critical thruster fails 5 seconds before touchdown? How does the AI respond if a sudden gust of wind on Titan pushes the lander sideways during its final approach? What if the primary radar system is blinded by an unexpected cloud of ice crystals kicked up from the surface? The simulation doesn't just run a perfect scenario, it runs every worst-case scenario imaginable, thousands of times over. This relentless digital torture testing allows programmers to refine the AI's decision-making logic, teaching it not just how to succeed, but how to gracefully and safely fail, maximizing the chances of survival even when everything goes wrong. It's a process of failing fast and failing often, but doing so in a universe made of code where every crash is a lesson learned and not a mission lost. But a computer simulation, no matter how advanced, can never fully capture the beautiful, chaotic complexity of the real world. This is why the next critical phase involves taking hardware out of the clean room and into environments on Earth that serve as brutal analog substitutes for distant moons. One of the most valuable testing grounds is found in the eternal night of Earth's polar regions. During the long winter months in the Arctic or Antarctica, teams from space agencies conduct field tests under conditions of extreme cold and perpetual darkness that are the closest analog we have to the surface of Europa. Here, prototype rovers and landing systems are deployed onto real ice sheets, riddled with hidden crevices and unpredictable surfaces. Engineers bundle up in massive parkas to watch as their machines attempt to navigate using only their onboard LIDAR and radar, validating the sensor performance against the ultimate benchmark, reality itself. Another incredible testing environment isn't on land at all, but underwater. The buoyant, neutral gravity environment of a large water tank, like the Neutral Buoyancy Laboratory used for astronaut training, provides a fantastic way to simulate the low-gravity conditions of a small moon. Engineers can test deployment mechanisms for drills or robotic arms, observing how they move and interact with surfaces in a way that approximates the gentle tug of a world like Enceladus. These underwater labs allow for full-scale, hands-on testing of hardware that would be impossible to evaluate properly in Earth's strong gravity. A prime example of this rigorous, multi-layered testing philosophy is embodied by the work at NASA's Jet Propulsion Laboratory. They have constructed elaborate, warehouse-sized Mars yards landscapes of red sand and carefully placed rocks that mimic the terrain of the red planet. While designed for Mars, the principles are directly applicable to darker worlds. Rovers are driven through these yards blindfolded, so to speak, forced to rely entirely on their autonomous hazard avoidance systems to navigate the obstacles. Inside specialized thermal vacuum chambers, entire landers are subjected to the crushing cold and airless void of space, with banks of lights shut off to plunge them into total blackness, all while their sensors are activated and their performance is meticulously measured. This combination of digital simulation and brutal physical analog testing creates a feedback loop of continuous improvement. Every stumble in a sandbox, every misreading in a dark chamber, leads to a tweak in the software or a modification to the hardware, slowly forging these machines into robust, confident explorers ready for the ultimate test. This culture of rigorous validation, of leaving nothing to chance, is what builds the confidence to send a billion-dollar mission on a one-way trip to a world we've never touched. This monumental challenge of landing in darkness is far too vast, too complex, and too expensive for any single nation to tackle alone. The mission to touch down on a distant, lightless moon is not an American endeavor, or a European one, or an Asian one. It is a human endeavor. And it is being met with an unprecedented spirit of global partnership. Space agencies that were once fierce competitors in a Cold War space race are now finding that their greatest strength lies in collaboration, pooling their resources, their brainpower, and their unique specialties to overcome obstacles that would be insurmountable for any one country. This isn't just about sharing the astronomical costs. It's about creating a whole that is genuinely greater than the sum of its parts, combining the best of what each nation brings to the table. Leading this charge are the established giants. NASA brings its immense experience in deep space operations and its pioneering work on autonomous systems. The European Space Agency, or ESA, contributes incredible expertise in precision instrumentation and robotics, as seen with the Rosetta missions landing on a comet. Roscosmos offers unparalleled knowledge in building robust, long-lasting spacecraft and in the complex logistics of space travel, and they are now joined by a new generation of powerhouse agencies. The Indian Space Research Organization, or ISRO, has repeatedly demonstrated breathtaking innovation with its incredibly cost-effective and successful missions to the Moon and Mars. Meanwhile, the China National Space Administration, or CNSA, has rapidly advanced its capabilities, achieving stunning milestones like landing a rover on the far side of the Moon, a first in human history, and returning samples from an asteroid. These partnerships move far beyond simply sharing blueprints or data. They manifest in concrete, awe-inspiring joint missions that are the future of exploration. Consider the proposed Europa lander mission. This isn't just a NASA project. It's a concept that involves contributions from ESA and other partners, each agency offering specific instruments or technological components that they have perfected. Or look at Dragonfly, NASA's incredible rotorcraft mission to Titan. While led by the United States, its development and scientific payload benefit from international collaboration, with European and other scientists integral to the team. This shared model does more than just spread out the financial risk. It fundamentally accelerates progress. A problem that might stump engineers at one agency for months could be solved in weeks by a team on another continent with a different perspective or a unique piece of legacy technology from a past mission. This diversity of thought is perhaps the most valuable resource of all. Furthermore, this cooperation is essential for building the framework of responsible exploration. As we prepare to visit worlds that could potentially harbor life, we need a common set of rules. International partnerships force these crucial conversations, leading to standardized protocols for communication frequencies so our spacecraft don't interfere with each other, for safety measures to ensure a mission doesn't accidentally crash into and contaminate a pristine environment, and for the ethical handling of any discovery we might make. By working together from the beginning, we ensure that humanity's first steps onto these alien moons are taken carefully, respectfully, and for the benefit of all people on Earth. This collective approach transforms the mission from a national achievement into a global legacy, proving that when faced with the ultimate unknown, our species can choose unity over division, building a future in the stars together. And so we arrive at one of the most profound and sobering responsibilities that comes with this incredible power to explore, the ethical imperative to do no harm. This isn't just about engineering success, it's about moral stewardship. The moment we land on a world like Europa or Enceladus, we cease to be mere observers and become participants. We are entering environments that have been utterly isolated for billions of years, pristine time capsules that could hold the answer to whether life exists beyond Earth. And the greatest threat to the scientific integrity of these worlds, and perhaps to any native life there, is us. Or more precisely, the trillions of microscopic hitchhikers we could inadvertently bring with us. The fear is a concept known as forward contamination, the accidental transfer of Earth's microbes to another celestial body. Imagine the heartbreaking scenario. A lander touches down on Europa. Its drill carefully collects a sample from just beneath the ice, and its onboard laboratory detects clear, unmistakable signs of biological activity. The headlines would scream that we have found life, but then a devastating question would emerge. Are we looking at genuine Europan life, or are we simply seeing the results of a contaminant? A single, resilient bacterium from Earth clinging to a poorly sterilized screw could survive the journey, be detected by our exquisitely sensitive instruments, and completely confound the results. It would create a scientific nightmare, a discovery forever shrouded in doubt. We might never know for sure if we found something new or if we just found our own garbage. To prevent this, we must send our most advanced explorers not just as brilliant machines, but as the cleanest objects ever to leave our planet. This isn't just a scientific best practice, it's a matter of international law. The foundation is the 1967 Outer Space Treaty, a landmark agreement signed by over 100 countries, including all the major spacefaring nations. The treaty explicitly states that exploration must be conducted in a way that avoids the harmful contamination of celestial bodies. This legal framework forces space agencies to treat planetary protection not as an optional extra, but as a non-negotiable requirement woven into the very DNA of every mission. The Committee on Space Research, known as COSPAR, provides the detailed, constantly updated guidelines that turn this legal principle into practical engineering standards. For a mission to a potentially habitable world like Europa, the requirements are exceptionally strict. mandating an incredibly low probability that the spacecraft could introduce any viable Earth organisms. Meeting this staggering level of cleanliness is a Herculean task that begins on the factory floor. The assembly of a lander destined for an icy moon doesn't happen in a standard cleanroom. It happens in a near-sterile biosecure facility that rivals those used for manufacturing the most sensitive medical implants. Engineers don gowns, gloves, and face masks not just to protect the hardware from them, but to protect the hardware from the microbes we all shed constantly. Every component, from the largest solar panel to the tiniest microchip, is meticulously cleaned with solvents and alcohol, but that's just the start. The final, most crucial step is terminal sterilization. This often involves baking the entire assembled spacecraft, sealed in a giant oven, for dozens of hours at temperatures high enough to kill even the most stubborn, heat-resistant bacteria. For components too delicate to survive such heat, alternative methods are used, such as bathing them in powerful doses of radiation or using specialized chemical gases that can penetrate every nook and cranny without causing damage. The design philosophy itself is also geared toward protection. Engineers will intentionally design systems to minimize contact with the pristine environment. A drill might have a mechanism to isolate its internal parts, which couldn't be fully sterilized from the sample it collects. The landing legs might be designed to avoid piercing too deeply into the ice. Every decision is weighed against the potential for introducing contamination. It's a painstaking, expensive, and absolutely vital process. It is the manifestation of a promise we are making to the universe that we will approach these new worlds not as conquerors, but as careful, respectful guests. Beyond the immediate scientific concern of contamination lies a deeper, more philosophical, ethical debate. If we were to discover life on one of these moons, what are our obligations toward it? Does extraterrestrial life, even if it's just microscopic, have intrinsic rights? The current planetary protection protocols are designed to protect the science, to protect our ability to study that life. But some ethicists argue we need a framework that considers the protection of that life for its own sake, a form of interstellar conservation. Should we establish permanent, inviolable sanctuaries on these worlds, regions where no drilling or exploration is ever permitted to allow any potential ecosystems to develop without our interference? Our actions now, as we take our first tentative steps into these environments, could set a precedent for centuries to come. We are navigating uncharted ethical territory, balancing our insatiable human curiosity with a profound duty to preserve the cosmic wonders we are only just beginning to comprehend. This careful, cautious approach is what will allow the stunning missions on the drawing board to become a reality. After years of simulation and testing, these incredible technologies are now being forged into real spacecraft, each one a monument to human curiosity and engineering prowess. Leading the charge is NASA Europa Clipper, a mission solely dedicated to unlocking the secrets of Jupiter's enigmatic ice moon. Scheduled for launch in the coming years, Clipper is not a lander itself, but its role is absolutely foundational. It will conduct dozens of close flybys of Europa, using its powerful suite of instruments to meticulously map the surface in unprecedented detail, measure the thickness of the icy shell, and even sample the composition of those tantalizing water plumes erupting into space. Think of Clipper as the ultimate scout. Its primary mission is to find the perfect parking spot, the safest, most scientifically interesting location for its eventual successor, the Europa lander, to touch down. The data Clipper sends back will be the final, critical piece of the puzzle, allowing engineers to refine the landing algorithms with real-world information, turning simulated maps into a concrete flight plan for a vehicle descending into the unknown. Building directly on that reconnaissance is the ambitious Europa lander concept, a mission that represents the absolute apex of everything we've discussed. This is the machine designed to do what once seemed impossible: touch down gently on Europa's chaotic, irradiated surface. Its entire design is a love letter to the challenges of dark landings. It will be equipped with a version of the autonomous landing hazard avoidance technology, using LIDAR and other sensors to pick its way through a treacherous landscape of ice ridges and crevices in real time. Its landing system will need to be robust enough to handle an uncertain surface composition, and its entire body will be radiation-hardened to survive in the hostile Jovian environment. Once down, its mission is even more breathtaking. The current concept includes a sophisticated drill designed to penetrate perhaps several feet into the ice to retrieve samples that have been shielded from the surface radiation, samples that might just contain the preserved biosignatures of life from the ocean below. This isn't just a landing, it's an attempt to reach out and touch another world's biology. While NASA focuses on Europa, the European Space Agency is preparing for an equally grand tour of the Jovian system with its Jupiter ICE Moons Explorer, or JUICE, mission. Launched in 2023, JUICE is on a long journey that will culminate in a detailed survey of 3 of Jupiter's major moons: Ganymede, Callisto, and Europa. While it will also perform flybys, its ultimate goal is to become the first spacecraft ever to orbit a moon other than our own, settling into a precise dance around the giant Ganymede. JUICE carries a powerful ice-penetrating radar specifically designed to peer through the frozen crusts of these worlds, mapping the depth and structure of their subsurface oceans from above. The lessons learned from operating JUICE's sensors in the intense radiation environment around Jupiter will be directly fed into the next generation of landing technology, providing invaluable data on how to see through ice and what kind of terrain future landers might expect to find. It's a vital Pathfinder mission, proving the long-term survivability and scientific capability of our tools in the outer solar system. Perhaps the most audacious and visually stunning of all these planned missions is Dragonfly. Destined for Saturn's moon Titan, Dragonfly throws the entire concept of a traditional landing out the window. Instead of a static lander, it is a revolutionary nuclear-powered rotorcraft, a large drone designed to fly through Titan's thick, hazy atmosphere. The darkness on Titan is a deep, perpetual twilight, but the moon's atmosphere makes radio and radar communications more reliable than near airless moons. Dragonfly will use this to its advantage, landing initially at one site like a traditional spacecraft, but then taking to the skies to fly tens of miles to a completely new location, turning a single landing into an entire expedition across a diverse world. It will touch down in areas of interest, from the organic rich sand dunes to the floor of an ancient impact crater where liquid water may have once mixed with surface organics. At each site, it will use a drill to sample the surface material and analyze it in its onboard laboratory, essentially acting as a mobile field geologist and chemist on a world a billion miles away. Dragonfly doesn't just overcome the challenge of dark landings, it transcends it, using the very atmosphere that creates the darkness as its highway for exploration. The common thread weaving through all these missions is legacy. Each one stands on the shoulders of the giants that came before. The parachute descent and surface operations of the Huygens probe on Titan taught us invaluable lessons about navigating thick, alien atmospheres that are directly applied to Dragonfly's design. The precise orbital maneuvers and long-term reliability of the Cassini orbiter provided the operational blueprint for the Europa Clipper and JUICE missions. The daring landing of the Curiosity and Perseverance rovers on Mars, using their sky crane maneuver, proved the viability of the complex, rocket-powered descent architectures that will be essential for setting down on airless moons. Every success and every failure from past missions has been meticulously studied, their lessons encoded into the very DNA of these new explorers. This iterative process of learning and improving is what transforms science fiction into science fact, turning the seemingly magical idea of landing in total darkness into a carefully calculated, tested, and achievable engineering plan. With launch dates stretching through the next decade, we are on the cusp of a new golden age of exploration, one that will see these incredible machines begin their long journeys to answer some of humanity's oldest questions. Yet even as missions like Dragonfly and the Europa lander move from the drawing board to the launch pad, a new wave of innovation is already taking shape in laboratories and research centers around the world, technologies that promise to revolutionize dark landings all over again. Imagine a sensor so precise it could detect the subtle gravitational tug of a hidden underground ocean, or a landing leg that could sense a crack forming in its own structure and instantly repair it using embedded microcapsules of healing agent. This isn't the distant future. These are the active frontiers of research that will define the next generation of exploration, pushing far beyond the already astounding capabilities we have today. One of the most exciting areas of development is in quantum sensing. Traditional accelerometers and gyroscopes in an inertial navigation system, while incredibly advanced, are still fundamentally limited by classical physics. Quantum sensors exploit the bizarre and counterintuitive properties of quantum mechanics, like superposition and entanglement, to achieve a level of precision that seems almost magical. An atom interferometer, for example, uses laser-cooled atoms falling in a vacuum as its reference. Because these atoms behave as perfect quantum waves, their interference patterns are exquisitely sensitive to tiny changes in acceleration or rotation. A quantum accelerometer could measure changes in velocity 1,000 times more accurately than the best systems available today, effectively eliminating the problem of drift that plagues current inertial navigation. For a lander descending onto a dark moon, this would mean it could know its exact position and orientation for days on end without needing a single external reference, navigating the void with a confidence we can barely imagine today. This quantum-level precision would also allow it to map the moon's gravitational field in real time during its descent, potentially identifying underground liquid water or caverns just by feeling the infinitesimal tugs on the spacecraft. Alongside these revolutionary sensors, a parallel revolution is occurring in materials science. The extreme cold of dark moons causes standard metals and composites to become brittle and fail. The answer may lie in advanced smart materials that don't just resist the environment, but actively adapt to it. One concept involves self-healing composites, materials embedded with tiny reservoirs of liquid monomer. If a landing leg suffers an impact and develops a microcrack, these reservoirs rupture at the site of the damage, releasing the liquid which then catalyzes and hardens, seamlessly filling the crack and restoring the material's strength. This could be the difference between a mission-ending structural failure and a simple, autonomous repair that allows the mission to continue. Even more futuristic are materials designed with adaptive thermal properties. These metamaterials can change their thermal conductivity or emissivity on demand, essentially acting as a smart blanket for the lander. In the extreme cold, they could reconfigure to trap every bit of precious heat generated by the RTG inside the spacecraft. If an instrument needs to be cooled to an even lower temperature for sensitive measurements, the material could then redirect heat away, all without any moving parts. This dynamic control over temperature would drastically reduce the power and weight needed for traditional heating and cooling systems, making landers far more efficient and resilient. Perhaps the most profound shift in strategy is the move away from single, monolithic landers toward the concept of swarm robotics. Instead of betting a multi-billion-dollar mission on one spacecraft nailing a perfect landing, we could send a coordinated fleet of smaller, cheaper, and more specialized robots. A mothership orbiter could release a dozen or more micro-landers, each no larger than a briefcase, to descend over a wide area. Some could be equipped with powerful seismometers to listen for moonquakes, while others carried drills for sampling or microscopes for imaging. They would communicate with each other using short-range wireless links, forming a local network that allows them to share data and coordinate their actions as a single, distributed scientific instrument. If one lander tragically topples into a crevasse, the mission isn't lost. The rest of the swarm simply reallocates the tasks and continues the exploration. This approach not only spreads the risk but also enables a type of science that is impossible for a single lander, such as creating a three-dimensional map of subsurface structures by using multiple seismometers simultaneously, or exploring the varied geology of a vast region in a single mission. To support these more ambitious and power-hungry missions, engineers are rethinking the very concept of power delivery. Solar power is useless in the dark, and nuclear batteries have practical limits. The solution might be to leave the power plant in orbit. Concepts for beamed energy involve a dedicated solar-powered satellite in orbit around the Moon, which would collect abundant sunlight unfiltered by an atmosphere, and then convert it into a tightly focused microwave or laser beam aimed precisely at the lander on the surface. The lander would be equipped with a rectenna, a special receiver that converts this beamed energy directly into electricity. This could provide a lander with virtually unlimited power, enabling high-energy experiments like powerful drills, long-distance roving, or even melting probes that could tunnel through miles of ice. Paired with this, optical laser communication would replace traditional radio waves for sending data back to Earth. Lasers can carry orders of magnitude more data in the same amount of time, allowing a lander to send back high-definition video streams, vast volumes of scientific data, and detailed topographic maps in minutes instead of hours or days. This combination of beamed power and lasercom would untether our explorers from their energy and bandwidth constraints, transforming them from short-term visitors into long-term, high-powered outposts. Underpinning all these hardware advancements will be the continued explosive evolution of artificial intelligence. The goal is to progress from the highly capable but still narrow AI of today toward a fully cognitive lander, an explorer that doesn't just avoid hazards but actually understands the scientific significance of what it is seeing. This next-generation AI would be trained on the entire corpus of terrestrial geology, chemistry, and biology. As it descends, its cameras and spectrometers would feed data into a neural network that could make real-time inferences. It might notice a strange colored patch of ice that matches the spectral signature of certain organic compounds found on Earth. Without waiting for commands from scientists light hours away, the AI could autonomously decide that this spot is a high-priority target, commanding the lander to divert its course and land right there. Once on the ground, it could then direct a robotic arm to collect a sample from that exact spot, prioritizing it over other, less interesting locations. This transforms the lander from a remote-controlled tool into a true partner in discovery, a field geologist with the combined knowledge of every Earth-bound expert encoded into its circuits, capable of seizing a fleeting opportunity for a monumental discovery that a human operator might have missed. These innovations, from quantum sensors to cognitive AI, are not just incremental improvements. They represent a fundamental leap in how we interact with the most remote and mysterious worlds in our solar system, making the incredible feat of a dark landing not just possible, but routine and profoundly rewarding. Mastering the art of landing in total darkness does far more than unlock the secrets of distant moons. It fundamentally reshapes humanity's entire future in space. The same autonomous navigation systems that allow a robotic probe to touch down safely on Europa are the direct precursors to the guidance computers that will one day land human colonists on the shadowed plains of the lunar poles or within the deep, dark canyons of Mars. These regions, permanently hidden from the sun, are not barren wastelands. They are treasure troves of critical resources, most notably vast deposits of water ice preserved in the eternal cold. The ability to land precisely and autonomously in such lightless conditions is the essential first step to accessing this water, which can be split into breathable oxygen and rocket fuel, effectively turning a distant outpost into a self-sustaining gas station for the solar system. This transforms the entire economic model of space exploration, reducing the crippling cost of launching everything from Earth and enabling a true, enduring human presence beyond our home planet. The technological ripple effects of this endeavor extend far beyond the cosmos, cascading back to Earth with tangible, life-saving benefits. The sophisticated sensor fusion that allows a lander to build a three-dimensional map of an unseen asteroid is already finding its way into search and rescue robotics. Imagine autonomous drones that can navigate the zero-visibility chaos of a collapsed building after an earthquake, using LIDAR and thermal imaging to locate survivors buried under rubble where human first responders cannot safely go. The robust, radiation-hardened computer systems designed to operate flawlessly for years on an icy moon are being adapted to create more reliable control units for deep-sea submersibles, exploring the alien, high-pressure darkness of our own ocean trenches. Even the algorithms powering the lander's real-time decision-making are informing the development of next-generation driver assistance systems, helping cars navigate safely through thick fog, blinding snowstorms, or other low-visibility conditions. The challenge of exploring other worlds forces us to invent solutions to extreme problems, and those solutions invariably find new purposes, improving technology and saving lives right here at home. Perhaps the most profound impact of conquering such a monumental challenge is the immense confidence it builds within the global scientific and engineering community. Successfully landing a spacecraft on a moon we've never touched, in conditions we can scarcely simulate, is a powerful testament to human ingenuity and perseverance. It proves that we can overcome seemingly impossible hurdles through innovation, collaboration, and sheer determination. This success creates a powerful momentum, building the technical and psychological foundation for even more audacious missions that currently reside in the realm of science fiction. The same nuclear power systems that keep a lander warm on Titan could one day propel generation ships on multi-century voyages to nearby star systems. The advanced artificial intelligence that guides a probe through a field of ice boulders could become the brain of an autonomous observatory sent to study an Earth like exoplanet light years away. Each successful dark landing is a stepping stone, proving that our reach can extend further than we ever thought possible. Ultimately, this progress represents something greater than the sum of its parts, a spectacular leap forward in our capabilities, driven by an international spirit of cooperation and a shared, innate human curiosity. It demonstrates that when we choose to focus our collective intellect and resources on a grand goal, we can achieve the extraordinary. These missions capture the public imagination in a unique way, creating a powerful narrative of hope and exploration that inspires a new generation of scientists, engineers, and dreamers. The children who watch a live stream of a landing on Europa today might be the ones designing the mission to an exoplanet tomorrow. This cycle of inspiration and achievement is perhaps the most valuable outcome of all, ensuring that the journey of discovery continues long into the future, pushing the boundaries of knowledge and reminding us all of our place in a vast and wonder-filled universe. It's easy to look at the mind-boggling complexity of landing on a dark, alien world and assume it borders on magic, or at the very least relies on a healthy dose of luck. This might be the most common misconception of all, that these missions are a high-stakes gamble, a billion-dollar roll of the dice where scientists simply cross their fingers and hope for the best. Nothing could be further from the truth. Every single aspect of a dark landing is the opposite of chance. It is the culmination of years, often decades, of meticulous planning, obsessive testing, and the deliberate engineering of redundancy upon redundancy. Think of it not as a gamble, but as the most carefully choreographed ballet imaginable, where every possible misstep has been anticipated and a contingency plan is already in place. The lander doesn't hope to avoid a hidden crevasse. Its systems are designed to detect it, map it, and navigate around it with a precision measured in centimeters, all autonomously. This isn't luck. This is the relentless application of physics, computer science, and human ingenuity, leaving absolutely nothing to chance. Another pervasive myth is the notion that these incredible missions are simply too expensive, that the billions spent on a single spacecraft represent a frivolous use of resources that could be better applied to problems here on Earth. This perspective misses the profound and tangible returns on this investment. The quest to land in total darkness forces us to innovate at the very edge of what's possible, leading to breakthroughs that ripple through our entire economy. The advanced artificial intelligence developed for autonomous hazard avoidance is already finding applications in self-driving cars, helping them navigate safely in blinding rain or fog. The miniature, radiation-hardened computer systems are informing the design of more reliable medical devices. The sophisticated sensors that can map a landscape with laser light are being adapted for use in archaeology and disaster response, helping to map unstable terrain after an earthquake. The financial investment in space exploration isn't just about collecting rocks on another world. It's a powerful engine for technological progress that benefits everyone, creating new industries and solving real-world problems in the process. The cost isn't an expense, it's a down payment on a future of greater capability and understanding. Then there's the fear that by handing over control to sophisticated artificial intelligence, we are somehow removing the human element from exploration, that these missions become cold, robotic affairs devoid of curiosity or passion. This couldn't be more wrong. The autonomy we build into these machines isn't about replacing human scientists, it's about extending their reach. It's the ultimate tool. Imagine a geologist standing on the surface of Titan, able to bend down and examine an interesting rock, then decide to walk over the next ridge to see what's there. A human can do that instinctively, but a remotely operated robot on a world with a multi-hour communication delay cannot. The AI and autonomy act as the scientist's proxy, granting the machine the ability to make those same instinctive, curious decisions in real time. The lander becomes an extension of the human mind, empowered to act on its scientific programming without waiting for a command that will take hours to arrive. This technology doesn't diminish the human role, it amplifies it, allowing a single team back on Earth to effectively be present on an alien world, making discoveries through a capable and intelligent partner. The thrill of discovery, the moment a new finding is beamed back to Earth, remains a profoundly human experience made possible by the silicon brains we sent ahead. Addressing these misconceptions is not just an academic exercise, it is vital for fostering the public support and engagement that makes these ambitious missions possible. When people understand that these are not reckless gambles but calculated endeavors built on a foundation of brilliant engineering, they can share in the excitement rather than the anxiety. When they see the practical benefits that flow from space technology into their daily lives, they can appreciate the value of the investment. And when they realize that these robotic explorers are the envoys of human curiosity, they can feel a sense of ownership and pride in each successful landing. Building this understanding transforms the public from passive observers into active participants in the grand journey of exploration, ensuring that we continue to push the boundaries of knowledge and strive for the next incredible horizon. Hearing from the visionaries who are actually designing our future in space brings an entirely new dimension to this incredible endeavor. Dr. Ellen Stoffen, whose career has spanned from analyzing radar data of Venus to serving as NASA chief scientist, perfectly captures the mindset shift required. Her point about rethinking robotics and sensing gets to the very heart of the matter. This isn't just about making incremental improvements to existing technology. It's about a fundamental paradigm shift, a complete reinvention of how a machine perceives and interacts with a world that offers none of the familiar cues we take for granted. It forces innovation in a way that a less challenging environment never could. This grand challenge, as she calls it, is a catalyst that pushes entire fields of engineering and computer science forward at an accelerated pace, with breakthroughs that will undoubtedly find applications we haven't even imagined yet. Then we have the perspective of Dr. Robert Zubrin, a renowned aerospace engineer and tireless advocate for human exploration. He looks past the immediate robotic mission and sees the foundational work for humanity's next great migration. The technologies being perfected for these dark landings, the autonomous navigation systems, the robust power sources that work in perpetual night, the hazard detection algorithms, are precisely the tools we will need to establish outposts on the Moon and Mars. The permanently shadowed craters at the lunar poles, which harbor vast deposits of water ice, are essentially dark landing sites. Mastering the ability to operate in such environments is the key to unlocking those resources, which can be turned into breathable air and rocket fuel. Zubrin's insight reminds us that these robotic missions are the first crucial steps in a much larger journey, paving the way for human pioneers to follow. What both of these experts underscore from their different vantage points is the profoundly collaborative and visionary nature of this work. It's a breathtaking blend of raw ambition and meticulous, practical engineering. It requires dreaming about touching an ocean world a billion miles away while also worrying about the tensile strength of a specific bolt and its reaction to extreme cold. This endeavor brings together astrophysicists, computer scientists, mechanical engineers, biologists, and materials experts in a unified effort to achieve what was once confined to the pages of science fiction. Their work is building a bridge from our world to others, and the exciting part is that this isn't a closed conversation among a select few. This is a human adventure, and there are countless ways for anyone with a spark of curiosity to become a part of it, to follow along and even contribute to these monumental discoveries. The incredible thing about this journey into the darkness is that it isn't just for the scientists and engineers at mission control. It's a story that belongs to all of us, and there are so many ways you can become a part of it right now. Staying connected is easier than ever before. The major space agencies are incredible at sharing their work in real time. Following NASA, the European Space Agency, or private companies like SpaceX on social media platforms gives you a front-row seat to mission launches, stunning raw images from other worlds, and live streams of control rooms during critical events. It's like having a backstage pass to the greatest show in the universe, but don't just be a passive observer. many of these organizations host free public lectures and webinars featuring the very engineers and scientists designing these missions. You can often submit your own questions and get them answered by the experts driving this work forward, turning a distant concept into a personal conversation. If you're feeling more hands-on, the world of citizen science offers a direct pathway to contribute to actual research. Platforms like Zooniverse host projects where you can help professional astronomers by looking through real telescope data to classify galaxies, or scour images from the surface of Mars to help identify unusual geological features. There are projects focused on searching for exoplanets or tracking asteroids, all using the power of crowdsourced human pattern recognition that even the best algorithms can't yet match. You might not be in the lab, but you could be the person who spots something everyone else missed, making a genuine contribution to our collective knowledge from your own home computer. For those who want to dive even deeper, a wealth of educational resources is available at your fingertips. Top universities around the world offer free online courses in subjects like robotics, orbital mechanics, astrobiology, and astronomy. You can learn the fundamental principles that govern these missions from the same professors who are training the next generation of aerospace engineers. This isn't just about watching a video, it's about building your own understanding piece by piece. Furthermore, supporting advocacy groups like the Planetary Society is a powerful way to have an impact. These organizations work tirelessly to promote government funding for space science, ensuring that missions to Europa or Titan remain a priority and that the resources are there to turn these breathtaking concepts into reality. Your voice and support help protect the future of exploration, and for the students watching or those considering a career change, this field is hungry for passionate, curious minds. The path to working on these missions is through degrees in engineering, computer science, physics, or planetary geology. But it's not just about building rockets. We need artists and animators to visualize the unknown, writers and communicators to share the stories, and policy experts to navigate the international partnerships that make it all possible. The journey to touch down on a distant, dark moon is one of the most ambitious things our species has ever attempted, and it truly is a collective effort. Every like that shares a mission's photo, every question asked at a public talk, every asteroid classified by a volunteer, and every student inspired to study the stars adds another thread to the tapestry of this grand endeavor. You don't have to wear a flight controller's headset to play a part in writing the next chapter of human exploration. And so our journey through the void comes to a close, but the story of dark landings is only just beginning. We've ventured together into the profound blackness of alien moons, exploring the monumental challenges of navigation without light, survival in crushing cold, and the need for absolute autonomy across unimaginable distances. We've unraveled the brilliant technologies rising to meet these obstacles, the artificial intelligence that serves as a pilot's mind, the symphony of sensor fusion that creates vision from nothing, and the robust nuclear hearts that power these incredible machines. These aren't just incremental improvements, they represent a fundamental leap in how we interact with the cosmos, transforming what was once pure science fiction into a carefully calculated, achievable engineering plan. These advancements are far more than a collection of clever gadgets. They are a powerful testament to humanity's most defining trait, our relentless, insatiable curiosity. It is that deep-seated drive to know what lies over the next horizon, to answer questions that have haunted us for millennia, that fuels this audacious endeavor. Every line of code written for an autonomous landing system, every sensor hardened against radiation, every watt of power coaxed from a pellet of plutonium is an expression of our collective desire to understand our place in the universe. The missions now preparing for launch to Europa's hidden ocean, to Titan's methane rivers, and to the other mysterious moons of the outer solar system are poised to do more than just collect data. They are ready to fundamentally rewrite our textbooks on planetary science, chemistry, and perhaps even biology, offering us a new origin story for life itself. Remember, the significance of each successful touchdown in that eternal night extends far beyond a single scientific paper. Every safe landing is a crucial step toward answering the profound question of whether we are alone in the cosmos, of finding a second genesis of life right here in our own solar system. And simultaneously, it is a step toward unlocking the practical resources, the water ice hidden in permanent shadow, that will serve as the propellant and sustenance for humanity's future as a multi-planetary species. This dual purpose, the pursuit of pure knowledge hand in hand with the enabling of exploration, is what makes this work so vital. Thank you for embarking on this deep dive into the future of space technology with me. If this glimpse into humanity's next giant leap captured your imagination, please show your support by liking this video and subscribing to the channel for more journeys to the frontiers of science. I would truly love to hear your thoughts in the comments below. Which of these moons are you most excited to see us explore? Until our next adventure into the unknown, this is your reminder to always keep looking up.